Hi, this is Dr. Habib Ahmed. Welcome to today's video where we will explore Origin software. Origin is a versatile tool for data analysis and graphing used by scientists and engineers worldwide. Origin, developed by Origin Lab Corporation, offers a comprehensive suite of features tailored for visualizing, analyzing, and interpreting data. With robust data analysis capabilities, Origin enables users to perform complex tasks like curve fitting, statistical analysis, and peak analysis. Whether you are in research, industry, or academia, Origin provides the tools you need to create publication quality graphs and presentations. Stay tuned as we dive deeper into Origin's features and capabilities. Don't forget to like, subscribe, and click the bell icon for more updates. So these are the kind of figures that we are going to plot in the Origin software today. Mostly these represent scientific data that we actually gathered from different experiments. So let me start with plotting the simplest of the figures. And so we actually performed measurements, current voltage measurements on some of the samples, and I'm going to show you how to perform the plot for the current voltage characteristics of the contacts of a simple film, semiconductor film. So starting with that, here is my Origin software. I open the sheet, and then as I told you, I actually performed different measurements, but here I'm going to talk about just one measurement at this point. I open this file, and then I am pressing Ctrl plus A at the same time, and then Ctrl C to copy that data. And over here I am pressing Ctrl plus V in order to paste the data over here in Origin. And now my independent variable is voltage. So I enter that information over in there in this column in the long name tab, and then for the units I would just enter volts. Similarly, in the second column, my dependent variable is current, and its unit is amps. So now I have all the information into this sheet. In order to plot this information, I click on the first column, and then I click on the second column. So now I've selected both these columns. Then I go to this icon, click on the icon, and then click on line plus symbol. Let me extend this graph. Okay, so now what we are going to do is we can perform different tasks with this graph. For example, the first thing I want to do is show the top axis and the right axis in this figure. So I go to this tab, show, and then I click on show top axis, and similarly I would definitely show the left axis and the right axis. Then I hit apply and click OK. So now you can see the top axis and the right axis as well. I don't want to see the numbers in the top axis and also the label on the top axis, so we can just click on this label and then hit delete. Similarly, we can click on this top axis and hit delete once again. Similarly, we can click on the right axis and hit delete, and similarly we can click on the right label and hit delete. This is the legend for the figure, and here we can rename it to IV characteristics. We also have control over the font of this legend, so I can set it to bold, and then I can increase the font size for the legend as well. So I have set it to IV characteristics. After that, we can do the same for this left axis, which represents the independent variable. So once again, I got to write it down. Current energy unit is amps. Select all the text. We can set it to bold, and similarly we can increase the font size to, for example, 28, and do the same for the x-axis as well. Choose all the text, set it to bold, and increase the font size, for example, to 28. Similarly, so also we have control over this vertical and horizontal axis as well. So we can go to scale, and on the scale, for example, or we can go to tick labels, and we can set this axis to scientific, and then hit apply. So like now we can see the numbers in the powers of 10. So and then similarly we can go to scale, and now here is here is where you can like set the increment from. Like for example, it's incrementing at a value of 2 into 10 to the power minus 6. So we can set it to, for example, 1e minus 6 over here, and then hit apply. So now it's incrementing at 1e minus 6. In fact, 2e minus 6 is a reasonable number, so we're going to go back to that number. Furthermore, over here you see the major ticks. So like this increment number actually represents the major ticks. Similarly, we also have the minor ticks over here as well. Right now between the major ticks we just have one minor tick. We can increase this number to, for example, 4, which gives a good view of the horizontal and vertical axis. We can do the same for the horizontal axis as well. So we can go to scale. My voltage is running from minus 5 to 5 volts instead of minus 6 to 6 volts. So I'm gonna set my voltage in the range of minus 5 to 5 volts. Similarly, this increment number for the major ticks is 2 volts, but we can also set it to, for example, 1 volt. And now you see my range is my voltage sweep is in the range of minus 5 to 5 volts. Similarly, for the horizontal axis, right now we have just one minor tick between two major ticks, but we can increase this number to 4 as well and hit apply. So we have increased the number of minor ticks between the major ticks to 4 at this point. Also, we can click on the horizontal axis and we can set it to bold, and similarly we can increase the font size as well for the horizontal axis and for the vertical axis as well. Also, so we can double click on this trace, and here we have control over the symbol type. For example, we can set the symbol to circular form. So now it has switched to circular form. Similarly, we have control over the symbol size as well. Right now the size is 9. We can set it to, for example, 5 and hit apply. So the symbol size has been reduced. Similarly, we have control over the symbol color. I like the blue color more, so I'm gonna set it to blue color, and we hit apply. We go to the line tab. Here we can adjust the thickness of the line. For example, I can set it to 2 and then hit apply, or we can set it to 4 and then hit apply. We can also set the colors of the vertical and horizontal axis. For example, you can set the color of that to blue as well. You can set the color of the horizontal axis to blue as well. Similarly, you can set the color of this label. You can set it to any color, like if blue, everything, not this one. So if everything blue works for you, you can set it in fact to blue. It's your choice. Okay, cool. So we have plotted the IV characteristics of a sample. Now in order to save the figure, you go to File, Export Graph, Open Dialog, and we can rename it to anything. For example, 222 underscore I versus V, or you can say IV characteristics, and then set the path of this one to the respective folder. And then click OK, and then OK once again. So now here is our saved figure. Here are the current voltage characteristics of the sample that we took the measurements for. Also, there is one more feature that I forgot to talk about. So if we go to exporting graphs once again and open dialog box, you can see DPI, dots per inch. It defines the quality of your figures. Some journals have a requirement that you have to submit DPI 300, DPI 600 figures to them. So you can save the figures with that corresponding quality. The higher the DPI number, the larger the size of the file would be. There is one more feature that we can add to this figure. For example, sometimes you have to perform fitting on your curves. So for fitting, we can go to Analysis, and then we can go to Fitting. We have different options. We can perform linear fit, polynomial fit, exponential fit. Exponential fit, for example, works in certain scenarios. For example, if you are working on doped samples, and then in order to calculate the activation energy on those doped samples, you have to measure temperature dependent doping concentrations for the sample, and then draw a figure where you have to plot natural log of the doping concentrations versus inverse of the temperature. It gives you an Arrhenius equation. On that Arrhenius plot, you can apply exponential fit, and this is going to give you the activation energy for your doped sample. In this scenario, even a simple linear fit is going to work. So we go to Analysis, then we go to Fitting, and then we perform linear fit onto this figure. Click OK. I go back to this figure and extend this table over here. So here is the equation: y is equal to a plus bx. So it's the equation of a straight line. Y is equal to mx plus c, where b over here represents the slope of this line. A represents the intercept of this line. So here is the slope, 1.63754 10 to the power minus 6. What does the slope tell us? The slope actually over here is the ratio of the change in current divided by the change in voltage. Now if you focus on the simple Ohm's law is actually V is equal to IR. Then resistance is the ratio of voltage to current. But here in this case, it's the opposite. Here the slope is telling us about the ratio of the change in current to the voltage. So this slope over here actually is giving us the conductance of this sample. And if you want to find the resistance, just take the inverse of it. It's going to give you the resistance. The resistance over here is going to be like slightly less than 1 mega ohm. Now this is an undoped gallium nitride sample, and definitely we are expecting it to be semi-insulating. So it's a highly crystalline sample grown with metal modulated epitaxy, an advanced version of molecular beam epitaxy at Georgia Institute of Technology at Professor William Allen Doolittle's group. The name of the group is Advanced Semiconductor Technology Facility. So definitely expect high quality samples from that group. If it is unintentionally doped sample, then you should definitely expect high resistivity from this sample and low carrier concentration. So if you know about how gallium nitride works, so this is how you perform fitting onto a plot inside the Origin software. Now there is other kind of stuff that we can do. Like for example, here is the sheet. So here is a linear fit. So I'm gonna move this, and here is the curve fitting. Next, I want to show you how to draw semi-log plots in the Origin software. So for that, I've chosen another sample where we have performed secondary ion mass spectroscopy on one of our samples, and here we have doping profiles for different contaminants on those samples. So I'm more interested in looking at the oxygen profile versus depth. These two columns, column I and J. J represents oxygen concentration and I represents the depth profile. So I'm going to choose these two columns, and then I copy these two columns. Here I am going to delete the information inside this sheet. So in order to delete the information, you just click on that particular column and hit delete on your laptop. Then hit delete for column B as well. Here I'm going to change the labels. I am looking at Sims concentration, and the x-axis is the depth, and on the y-axis I am actually looking at the Sims concentration. The unit of depth is micrometer. So in order to include micro, you right click over here and then go to insert, go to symbol map, click on the micro symbol and then click on insert. And the unit for Sims concentration is per centimeter cube. So make -3 a superscript. Then over here I just click on this tab and hit Control plus V in order to paste the data that I copied from this Excel sheet. And now I can close the Excel sheet. Okay, so now in order to plot this data, I select both columns and then I go to this icon and then click on line plus symbol. As you can see, this kind of looks like a random figure at this point. We cannot really figure out the information inside this figure. So I'm gonna perform some settings in order to look for information, like critical information inside this figure. So the first thing I'm gonna do is I'm gonna change the y-axis to logarithmic, and the information is in the range of approximately 117 to 2 into 10 to the power of 20 per centimeter cube. Then we hit on apply. Well, slightly less than 117. Let us see if it is 116. So almost, but I mean, let us do like 2015. Okay, this is gonna work. Also, for the horizontal axis, I'm more interested in looking at information in the range of 0 to 5 micrometers. So I set the scale for the x-axis as well. Similarly, I want to have 4 minor ticks between the major ticks. So I hit apply, and as you can see now, between the major ticks we have 4 minor ticks. Similarly, I'm going to do the same for the vertical axis as well. So instead of 8, I want to see 9 ticks, which is the general pattern that you want to see in logarithmic plots. Similarly, I want to show the top axis and the right axis as well. Move this over here. Then at this point you can perform different things, like as I already told you, you can set it to bold, you can increase the font size. Similarly, you can do the same for the x-axis as well. For this we have to redefine it. Right click over here in order to insert a symbol. Click insert. So we inserted micrometer over here. Set it to bold, and we can further increase the font size. Similarly over here we reintroduce Sims. And increase the font size. So if at some point your figure gets hidden, you just have to move around the windows in order to look for your figure. You can set it to full screen, and then you can minimize these windows as well. Like for example, you can set it to full screen and then you can minimize it from here. Okay, we can set this axis to bold as well, at the same time increasing the font size, and the right axis as well. Cool. Now I double click over here on this trace, and I don't want any symbols over here on this curve, so I'm going to set the symbol size to 0, and then I hit apply. So now, and then click OK. So now you can see that the symbol size has the symbols have been eliminated. Also, you can go to line and we can set the thickness of this trace to 4. Also, so the way I'm doing it, I go to the trace and then I double click on the trace. So similarly, you can set the line color to any other color. We can set it to blue and hit apply. So now this gives you the Sims concentration profile for the oxygen Sims concentration profile versus depth for your sample. And then once again we can save the figure, like we can go to File, Export Graph. We can set the quality of the figure to 300 dpi, 600 up to 1200. Rename it to Sims. Define the path for this figure and click OK. Then click OK once again. Then go to the respective folder, and here is our Sims concentration profile figure. So I'm gonna save this project as Sims, and I'm going to move on to the next one. So now I'm going to show you how to include multiple current voltage characteristic plots into the same figure. In this regard, I've got multiple samples, like the same sample with multiple measurements. And what we can do is we go over here and delete the previously saved information. Once again we are dealing with voltage and current. So we set the label for the independent and dependent variable, and now at this point I've got 6 different measurements. I open the measurements, hit Control A and then Control plus C, and then paste the information over here. Now, in order to include the rest of the measurements, we need to include more columns over here inside this Origin project. So in order to include more columns, you click on the rightmost column and then press Control plus D. Once again I repeat, Control plus D. D as in doctor. So I press Control plus D and then click on yes. So I need to include the results for 5 more measurements. So I'm going to include 10 more columns. 2 columns for each measurement, one for the independent variable and the second one for the dependent variable. So I click on OK. So now I got so many different columns, and so now one by one I'm going to copy these measurements and paste them over here inside these inside this sheet. So over here, this is my independent variable and this is my dependent variable. So I'm gonna set column C to X, which represents independent variable. So similarly, column D is set to Y, which means that this is a dependent variable. Similarly, I'm gonna copy the measurements of the rest of the files. Okay, so column E is an independent variable, so I have to set it to independent variable. You can choose this X over here, or you can click on this one. Similarly, column G also represents the independent variable, I also represents the independent variable, and K also represents the independent variable. So at this point now, you have got two approaches. One approach is to choose all these columns and then go to line plus symbol, and this gives you the IV characteristics of these results. Another approach is if you focus closely on this sheet, you will find out that the independent column for all these measurements is the same. Like we've got -5 over here, -5 for all the independent variables. Similarly, -3.99, 3.99, 3.99. So all these are the same. So we don't really need the extraneous columns. So what we can do is we can click on the extraneous columns and we can just click on delete. So now we have 6 independent measurements versus this dependent variable. And once again, you can choose all these columns, go to line plus symbol, and here you plot the IV characteristics. And if you compare this one with the previous one, these two are exactly the same. So I'm gonna close the previous one. Okay, and then at this point I can play around with the scales and the traces in order to perform the settings, starting with the X and Y axis. Now we can adjust the scales. So first of all, we can show the top axis and the right axis as well. Hit apply. Then I don't really like the label and these numbers on the right and on the top scale, so I'm going to delete these. We can label them as measurement B, C, D, E, F, and G. Or you can start from A up to F. So it's your choice. Okay, then I double click on this vertical axis and I click on this decimal and I set it to scientific instead of decimal. Similarly, I go to scale and introduce 4 minor ticks between the major ticks instead of 1. Similarly, I click on horizontal scale, increment it by 1 volt instead of 2, hit apply. Similarly, the measurements are in the range of -5 to 5 volts, so you can set the range, and similarly we can increase the number of minor ticks between the major ticks. So hit apply for that as well. So we have got these measurements. Now you can further play around. Before that, we can set these axes to bold as well. And similarly, you can click on one of these traces, and for example, then you can like reduce the symbol. So you can remove the symbols from these traces. So the way to do it is you got two options. First of all, if you click on this independent option, then you go to symbol, you set the symbol size to 0. It's going to, like, you see this trace over here, this one, or instead of this one, this is not really obvious. So instead of that one, I'm gonna do it for the last one, which is more obvious. So once again, I've set it to independent. I set the symbol size to 0, hit apply. So now you can see it has eliminated the symbols just from this curve, but not from all the curves. So we can repeat the process and do it for all the curves, but another option would be go to group and make them dependent on each other, then go to symbol, and so like first of all we have to reset this option first of all. Then you go to group, make them dependent on each other, go to symbol, so we have to, we have reset the option by using Control Z option. Then we go to group, make them dependent on each other, go to symbol, and for symbol you can set like the symbol to anything. In fact you have to click on the layer, and then on this one make them independent, make them dependent on each other. We can do like this as well. We can click on the line option from here. So this is one way to do it. And then we can increase the thickness to 4 for all these figures. So we have grouped them together, and then we have increased the thickness of all the traces inside these plots. And then finally you can go to File, Export Graph, and follow the steps that we have previously discussed in order to save this plot. So at this point I'm going to close this project. Now similarly I have performed similar measurements on other samples as well, but these are not IV characteristics. These are actually photoluminescence measurements. So here my independent variable is actually energy, ranging from 3.4 to 4 approximately 4.7 electron volts, and my dependent variable is actually intensity in arbitrary units, and I perform measurements for 1, 2, 3, 4, 5, 6, 7, 8 different samples. This is excess gallium dose for metal modulated epitaxy growth of gallium nitride films. If you are interested more in that, study our metal modulated epitaxy growth of UID gallium nitride films from Professor William Allen Doolittle's group. So in order to plot these photoluminescence measurements of these samples, I select all these columns. How do I select all these columns? By pressing the control button and clicking on each column simultaneously, and then I go to line plus symbol. I'm going to extend this window as much as possible. On the y-axis, my independent variable is intensity in arbitrary units. I'm gonna set it to bold and increase its font size. Similarly, on the x-axis, my independent variable is energy in electron volts. If you focus closer on these plots, the actual results are in the range of approximately 3.2 to approximately 3.55, I would say 3.2 to 3.6 volts. So I'm going to change this scale. Similarly, I'm going to set the minor ticks to 4 between the major ticks and click on OK. I'm going to set it to bold and I would increase its font size to 26. Similarly, I click on the x-axis and I set it to bold and increase its font size to, I would say, 22, and do the same for the y-axis as well. Okay, I double click on this vertical axis and I click on show. I want to see the right axis and the top axis as well, so I hit apply and click on OK. I'm going to delete these labels and move this legend over here to the left of these peaks. Okay. Okay, this is fine. I wanted to set it to bold, but I mean that is going to increase my effort. Then I double click on the traces, and here I know that they are grouped together, so I go to symbol and I reduce the symbol size to 0, which means that I don't want to see the symbols on this figure. So then I click OK. The thickness of these lines is not fairly enough, so I click on line at this point and increase the line size to 4. Now hit apply and click on OK. So these are actually the photoluminescence measurements for these samples, and here are the results. So at this point you can just save the figure and save the results. So next I want to show you, like, sometimes what happens is, let me move to the next folder. Normalized PL intensities. So sometimes you want to look at normalized X-ray results, like normalized symmetric and asymmetric rocking curves, and normalized photoluminescence measurements in order to perform a comparison about the peak position of these samples. Like for example, one example is given over here. So why is the peak position important in photoluminescence measurements and also in X-ray measurements? Because the peak position tells you about the crystallinity and about the type of the sample, and a shift in the peak position either to the left or to the right actually tells you about the compressive and tensile forces in this film, or in other words you can say about the stress and strain inside the thin films that you have grown using different growth techniques. So it is crucial to look at normalized peaks as well. So in order to do that, I'm going to show you the procedure to do that. In order to do that, so at this point, let me move this figure to over here. In order to do that, we click on all the independent variable columns, and then also on all the independent variable columns, and then I right click on these columns and click on normalize, then click OK. So to the right of these columns, now you got normalized columns for all these columns that we had before. For example, this column J is normalized to 1 monolayer. Here is the 1 monolayer column, which is column B. Similarly, K is normalized to 2 monolayers, which is column C. Similarly, L is a normalized column for D, and so on. So we have got all the normalized columns. Now, in order to plot these normalized columns, we select the independent variable column and all the normalized columns. And then we go to plot line plus symbol. Extend this one as well. And once again, our scale is going to be in the range of 3.2 to approximately 3.6 electron volts. Increase the number of minor tick counts between major ticks to 4. Hit apply and click OK. Then we can do the same, like my independent variable is intensity in arbitrary units. Similarly, my the y-axis represents the dependent variable, and my independent variable actually is energy in electron volts. Set it to bold and increase the font size of this independent variable as well. Similarly, set this axis to bold and increase the font size and also the vertical axis. So now, as you can see, that all the peaks are now normalized to 1 for comparison of the peak position of these samples. Once again, I'm going to double click on the axis and show the top axis and the right axis. Hit apply. Okay. uh, and then double click on the traces. They are grouped together. Go to symbol, reduce the symbol size to 0, hit apply, and then go to line and increase the thickness of the traces, and then hit apply once again. So now you see that when we normalize the samples, we see there is a shift in the peak position of these samples, representing compressive and tensile forces in these samples. At this point, you can save the figure. What else do we want to do? Stacks. Yeah. So sometimes, like for example, this is my poster that I actually presented in one of the conferences in Washington State at Bellevue. That was a wonderful trip as well. So if you zoom in on this poster, you might see these stacks for comparison. These are symmetric and asymmetric rocking curves for aluminum nitride films, and this gives you a good comparison about the peak position of the X-ray measurements for both symmetric and asymmetric rocking curves. So then from here you can say like the thicker films are complicated by partial relaxation and wafer bow, and similarly the thinner films they become complicated by strain and island coalescence, etc., etc. So you can draw like different conclusions from there. So now I'm going to show you how to plot stacks, and for that purpose what we are going to do is we do the same. Like, let us look at the normalized plots once again for the stacks. So select all select the independent variable column and all the normalized dependent variable columns. Then click on this icon and click on stack. Click OK and extend the size of this graph. Okay. Then I don't want to see like all these labels on the y-axis, so I'm just gonna delete them. Like, the goal is to perform a comparison of the peak position and not the intensity, because the intensity is normalized anyway. Similarly, we want to look at a range of 3.2 to 3.6 electron volts. Set the minor ticks counts to 4, hit apply and click on OK. And then the independent variable is energy in electron volts. And similarly, I'm going to move this label from here to over here. The dependent variable is intensity, normalized intensity. You can write normalized intensity as well. So now if you click on this, you would see this option like you can rotate the normalized intensity, and then you can move around it to fit it to a right position. Then okay, this is already set. You can click on this trace, or in fact different traces. So before that, so let us double click on the trace once again. Plot type line. We don't want line plus symbol. Okay, so what we can do is start doing it one by one. We can set the color and the thickness of each figure in this stack. You can do it from here as well. Click on this one, set its color to any other color. So many different options. Pardon me if you don't like my choice of colors. This is fine. And finally layer number 8. Okay, so you got the figure, and now you can just save the results. Export graph. Give it a path. Okay, and click OK once again. So here is the beautiful figure for publication purpose. Let me close this project now. I opened a lot of files in the meantime. Let me close them. Okay, so what else is left? I already performed the plotting of IV and semi-log IV characteristic, semi-log plot, not semi-log IV but semi-log plot. When we were looking at the Sims profile, it was actually a semi-log plot. Two things are left, how to introduce an equation, and then how to introduce a double y-axis. So this one is slightly simpler. So I'm gonna do this one first and then focus on the second one. Let me open this project. So let me tell you what I mean by introducing an equation. Like for example, here we have got two columns. We have the IV characteristic, the current plotted versus the voltage. Now, how about I introduce a resistance column as well inside this figure, and we don't have to perform all the measurements or do all the calculations manually. What we can do is we can just introduce a column to the right of this one. How do we do that? We click on this column, on the rightmost column, and then press Ctrl plus D, D as in doctor. Click on yes. We want to introduce just one column to the right. And here if you focus on this row, it is f of x is equal to. So here you can actually enter an equation. And for calculating the resistance, resistance is equal to voltage divided by current. So basically A divided by B is going to give you the resistance column for this one. So now you got the resistance column over here as well. So in order to include the resistance column, just hit apply. Let me see if it is introduced. So in order to do that, we actually need a double y-axis. Like the units of these are not the same, right? So what we need to do is we need to introduce a double y-axis plot. And in order to do that, for example, I'm going to delete this one. So I choose all these three columns, and then I go to this icon and click on double y-axis. So now we got the plot. So the left axis gives you current, the right axis gives you resistance. You can change this label. In order to insert a symbol over here, we right click over here and click on insert symbol map and look for ohm symbol over here and click on insert. Okay, so this gives us the, and then you can perform like the settings for these variables. You can set them to bold. In order to make this figure more obvious, let me set the color of everything which is related to the left axis as blue, and everything that is related to the right axis as red. So I'm gonna set the color of this label to red as well. Similarly, I'm gonna click on this one, set it to scientific, and at the same time I'm gonna set its color to blue. Okay, similarly for this one, I'm gonna set its color to blue as well. So okay, this is my current versus voltage plot. So let me reduce the symbol size to, for example, or we can leave the symbol as it is, just change the color of this one, and also just set the color. Also let me set the thickness to 4, and let me set the color to blue for this trace. Similarly for the resistance curve, the symbol color is fine, the line color is fine. Let me set the thickness to 4, and that would be it. So now here is our final figure. It's a double y-axis figure where we have plotted current versus voltage and resistance versus voltage onto the same figure. And at the same time, inside this project, we have introduced an equation as well. Now finally, here is a double y-axis figure as well, but this is a more complicated scenario. So, like, let me open the project. And initially when I was working on this project, it kind of gave me a tough time. So, okay, let us deal these section by section, and then we are going to put them together. So like these are kind of pieces of a puzzle. So let us look at these pieces individually, and then later we are going to put them together. Okay, so we have got an independent variable, which is beryllium concentration. Forget about the sample and about the significance of the sample. Just consider it a doped sample with doping concentration, where we have got these three values. And for these three values, we are looking at 1 over 1000 of the peak position and 1 over 10,000 of the peak position. So we are looking at two different independent variables. You can call this 1 over 1000 at dependent variable A, and you can call this 1 over 10,000 as dependent variable B. Now we've got 4 more samples, and for each of these 4 samples we have got one independent variable data point and one dependent variable data point. So for example, the doping is 1e17, and the dependent variable value is 2324 for variable A, or 1 over 1000. Similarly, the doping concentration is 2 10 to the power of 20 per centimeter cube, and the dependent variable value is 4907 for rocking curves. Similarly, we got 2 more samples where we have the result for dependent variable A and dependent variable B versus different. So here we have got a complicated scenario where we have independent variable with different values. Similarly, we have 2 dependent variables with so many different kinds of different samples. For these, for this sample, we have 2 columns, but for these samples we have just one data point for each variable versus the carrier concentration. So how do we put them together into the same figure? One thing is for sure, that we have got 2 dependent variables, which means that we need a double y-axis plot. We need a left axis and we need a right axis. But then how do we put them together into the same figure? So let me show you. So the first thing we do is we select all these columns. Okay, and then we click on this icon. We click on double y-axis icon, extend the size of this one. Okay, and this is independent variable, so you can just call it like 1/1000, the left axis, and set its color to blue, and similarly set the color of this scale to blue as well. Similarly, let's call this one 1/10,000, or you can also call it variable b, and let me set the color of this variable to red. Okay. Also, and the horizontal axis is on logarithmic scale, so I'm gonna set its scale to like 8e16, in the range of 8e16 to 2 10 to the power of 20, and by counts we are gonna keep 9 minor ticks between the major ticks. Hit apply. And this is not a linear scale, this is logarithmic scale. So hit apply once again. Okay. Let me name it to beryllium concentration per centimeter cube, and bring this -3 to the superscript. Okay, so everything which is related to the right axis, we are gonna set its color to red, and everything which is related to the left axis, we are gonna set its color to blue. But before that, let us find the y-axis range for the left axis and for the right axis. So let us look at the 1/1000 variable. 2400, 2400, 2300, 2300, 2200. So it's kind of in the range of 2200 to 2450. So let me set this range. Then hit apply. Now let us look at the right axis. So focusing on the right axis, 1/10,000 variable, 5000, 4800, 4700, 4900, 4700, 4900. So it's kind of in the range of 4700 to 5100. Hit apply. Now, in order to put all the puzzle pieces together, we double click on these layers. So first I'm going to double click on layer number 1, and on the left axis we want to display everything which is related to the 1/1000 variable. This is related, this one is for 1/10,000. So we are going to move the 1/10,000 to the left, and move everything which is 1/1000 to the right. Then hit apply and click on close. Okay. And then set its color to blue so that we know for sure that this is related to the left axis. Hit apply. Also the line color should set it to blue. How about the symbol? Well, the symbol is fine. Okay. Now double click on layer number 2, and on the right axis we want to see the 1/10,000 variable. So everything which is 1/1000 inside this chart, move it to the left and include the columns, like for example G, J, and what else is left? This column C. To the right, hit apply and click on close. So now double click on this one and set its size to 4. Okay. In fact, so this blue curve, we don't really need it in the range of 2200. You can set the scale from 2350 to 2450. No, actually no. There might be other values which might be missed. So first enter the color for everything. This is a 1/1000 variable, so I'm gonna set its color to blue and set its symbol to, for example, star, and we can increase the symbol size to, let us set it to 24. Okay, that's a wonderful star. Now let us focus on this one. Okay, this once again is a 1/1000 variable. Let me set a symbol to this one and its color to blue and its size to 24. Hit apply. Okay, click OK. So this is in the range of 2250 to 2425. Click on apply and hit OK. Or in fact, Control Z. This one gives a slightly better picture. Okay. On the y-axis, we can increase the minor ticks count to 4. Click on OK. Let us turn our focus to this symbol. It is a 1/10,000 variable. So its color is set to red already, which is fine. And we can increase its symbol size to 25. Also, what else? Click on OK. Okay, so now we have solved the puzzle. Now we have got these different samples and we have found the results for these samples. Okay. So all these two blue data points and this blue curve is related to the left axis, and these two data points and this red curve is related to the right y-axis. So this is how you put together results in Origin software. That's it for today. Thank you for watching our introduction to Origin software. We have only scratched the surface of what Origin can do for your data analysis and graphing needs. If you found this video helpful, please give it a thumbs up and share it with your colleagues. Don't forget to subscribe to our channel for more tutorials and guides on using Origin, Silvaco TCAD, and other nanotechnology projects that could enhance your research and projects. If you have questions or specific topics you would like us to cover, let us know in the comments below. Until next time, happy analyzing with Origin. Adios.